In this video, we're going to see how to calculate mass and centroid using double integrals. So here's the context. Let's say that we have a region in the xy plane. And as usual, we'll call that region R. So imagine that this represents a thin, flat plate. Could be something like a metal plate. And this is sometimes called a lamina, if we want to be formal. So lamina or just thin metal plate. Little delta is a function of xy and it represents the density at point xy. That little bit of thickness that the metal plate has is going to be built into the density. So the density only depends on the x and y coordinates. Second piece of notation, we want to introduce a point called x bar, y bar. And that is our notation for the centroid. Centroid, just another way of saying center of mass. So there are three formulas that we're going to use in this video. First one is for the mass of the lamina, and we'll call that mass m. So if we wanted to calculate the mass, we would do a double integral over the region, and what we would integrate is our density function delta, and we'd have our dA at the back to represent our dx dy. So when we write down these formulas, I like to think in terms of units just to convince ourselves that the formulas make sense. So delta, the density function, would be measured in units like kilograms per meters squared, for example. dA, because it represents dx times dy, this would be measured in units like meters squared. So when you take your kilogram per meter squared times meter squared, sure enough, you get kilograms. So units there hopefully make sense for the mass. Let's think about the coordinates of our centroid. So if we wanted x bar, formula is 1 over the mass times the double integral over the region R of x delta dA. So again, let's think of this in terms of units. Let's say that the xy coordinates are measured in units of meters, just to keep things simple. So we already said in the first part of in our mass discussion here that delta dA would have units of kilograms. So if we multiply by x, we've now got meters times kilograms, and then we divide by the mass. So that divides through by kilograms, leaving us just with meters. So units wise, hopefully that formula makes sense. So in a similar way, if we wanted y bar, it's just the exact same formula except replace the x with a y. So 1 over the mass, double integral over our region R, y delta dA gives us our y bar. So we're going to do a centroid calculation in a moment, but before we do that, we're going to talk about symmetry. Because if we have an understanding of symmetry in our region and symmetry in the function delta, then we can really take a big shortcut in a lot of these problems and not necessarily have to calculate both of x bar and y bar when we're finding our centroid. So there are three situations where we want to think about symmetry, and we'll just look at them one by one. So let's look at this heading here. This says, if our region R looks like, so suppose our region R is something that is symmetric about the line y equal x. For example, our region R could look something like that. And let's say it's also true that our function delta is unchanged when x and y are swapped. Then it's true that y bar is equal to x bar. So the idea here with symmetry is that you really need two types of symmetry in order to conclude that you have some sort of symmetry in your center of mass. You need your region R to have symmetry, but you also need that same type of symmetry in your function delta. And that type of symmetry says that if you take this point and you swap the x and y values, you get this point. So the idea is that you need these 2 points to have the same density. So that not only is the shape of your region symmetric, but your mass is actually distributed through that region in a symmetric way as well. Okay, so there are two other types of symmetry. There's horizontal and vertical symmetry. So let's think about the horizontal one. Let's say that our region is symmetric about the y-axis. So you've got all these pairs of points that are going to pair up, can reflect them through the y-axis like that. So we've got horizontal symmetry. And you would need delta to be unchanged when x is replaced with negative x. So that's just like saying if you take this point here and you flip it over the y-axis, so keeping its y value the same, but changing the sign of its x coordinate, you're flipped over to this point. And to say that delta is unchanged when x is replaced with negative x is just a way of saying these 2 points. We've got the same density at these 2 points. So if both those properties are true, then we can conclude that x bar is going to be 0. So your center of mass is going to lie somewhere along that y-axis. And then final idea, let's look at the situation of vertical symmetry. So if you have a scenario like this, where your region is symmetric about the x-axis, and if it's also true that our function delta is unchanged when y is replaced with negative y, then we're going to be able to pair up all the points in this region. So by symmetry of R, all the points will pair up. And because delta has that same kind of symmetry, if you take a point and just change the sign of its y value, delta's staying the same. So that's just a fancy way of saying our lamina has the same density at these pairs of points. And so because R and delta both have that same kind of symmetry, we can conclude that y bar equals 0, meaning the center of mass lies somewhere along the x-axis. So those are the types of symmetry that we're going to watch out for. We'll do a quick little example here to practice symmetry, and then we'll do a bigger calculation example. So we're just going to do a little practice example here around symmetry. Specifically, we're going to look at horizontal symmetry. So you can see we've got this region that is symmetric about the y-axis, just a nice rectangular region. So that means all these points in R are going to pair up. In fact, I guess if we're being really rigorous, all the points that are not on the y-axis will pair up with one another. Okay, now suppose we have some information about our density function. And so in each of these 3 different cases, we've got different density functions, and we want to see what we can conclude about x bar. So the thing we're supposed to ask is delta unchanged when x is replaced with negative x? Well, there's no x in this formula. So if you replace x with negative x, by definition, you're not doing anything to delta. So yes, delta is unchanged when we replace x with negative x. If you want to be really formal, you could write delta of negative x comma y is equal to delta of xy. That's just a fancy way of saying if you replace x with negative x, you get the same thing as your original function. So yes, that's true. And therefore, we can conclude that x bar equals 0. So when we say this part, that is like saying geometrically these 2 points have the same density. And that's going to be true for all the pairs of points in this region. So because the region has a symmetric shape and because delta is symmetric, we know that the mass is distributed in a symmetric way, and therefore the x-coordinate of the center of mass is going to lie along that midline, which is the y-axis. So x bar is going to be equal to 0. Okay, same deal here. In part B, if we replace x with negative x, so when we take negative x and we square it, we get x squared. So yes, we still have the same type of symmetry. Delta of negative xy is equal to delta of xy. And in a similar way, we can say, yes, x bar is going to be equal to 0. Okay, now part C is more interesting. If you replace x with a negative x, you get minus x plus 6, and that is not equal to our original function delta. So basically, geometrically, what's happening here, if you look at a point somewhere over here, let's say where the x value is negative 3, okay, our density at these points here is 3. Let's say 3 kilograms per meter squared. Okay, now as we move further over to the right and x increases, let's say we look at now x equal positive 3, well, our density function is now 9. So somehow we've got higher density as we move to the right, and that tells us that the mass is not distributed in a symmetric way. So for sure, x bar is not going to equal 0 here. So although the region itself has symmetry, the density function unfortunately does not. So you need both the region and the density function to have that symmetry in order to draw a conclusion about symmetry in the center of mass. So we're going to let C be a positive number. We're going to let our density function equal root x squared plus y squared. And we want to find the centroid of a certain region in the xy plane. Our region is the first quadrant of the disk. X squared plus y squared is at most c squared. Okay, so maybe let's start by drawing a picture of our region R. So x squared plus y squared equals c squared. Circle of radius c sitting at the origin. Incidentally, this is why we're told that c is greater than 0, just so we can say that c is our radius. And what we want is actually the disk and just the first quadrant of that disk. So there's our region R. And I'm going to erase the circle and just draw in the quarter circle there. All right, so let's think first about symmetry, because that will probably cut down the amount of work that we need to do. So our region, certainly symmetric about the line y equal x. And then let's ask if our function delta has the same kind of symmetry. So now let's look at our delta function. If we swap x and y, so just replace every x with a y and replace every y with an x, we would get square root of y squared plus x squared, which is equal to delta. Okay, so we could say that delta has the correct type of symmetry, and I'm going to record that just by saying by symmetry of R and delta, we can conclude that y bar equals x bar. So basically, geometrically, what we're saying is all the points in this region are going to pair up. All the points that are not actually on the line y equal x will pair up. Because of the symmetry of R, and because of the symmetry of delta, we know that for each of those pairs, the points will have the same density. So that tells us that the mass is distributed in a symmetric way about that line y equal x, meaning our center of mass will lie on that line, and therefore y bar will equal x bar. So the problem then comes down to calculating x bar. Let's start on that by calculating our mass. So to get mass, we need to do double integral over r of our density function. And you can choose whatever coordinate system you like. You could use rectangular coordinates, x, y, but I would suggest, because we have a quarter circle and because delta looks like square root of x squared plus y squared, polar coordinates would be a really good choice here. So if we want to move into polar, let's think about our region R. So the radius values captured in this region here, well, this is a circle of radius c. So the radius values in the disk are going to range from 0 to c, and the angles are going to range from 0 to pi over 2, because we're just doing that first quadrant. Okay, in terms of our integrand, delta, we're told in the question, is square root of x squared plus y squared, but if we move that into polar, that becomes r. And then dA in polar, r dr d theta. So that way, we're ready to rewrite our mass in polar coordinates. So here we go. Mass is going to be the double integral of, well, if we multiply delta times dA, we're getting r squared dr d theta. And then we'll just put our limits of integration on here. R is going from 0 to c, and theta is going from 0 to pi over 2. Okay, so let's get this integration done, and we'll have our mass. So integral from 0 to pi over 2, we'll keep our d theta on there. We're going to integrate r squared to get r cubed over 3, and that's going to be evaluated at r equals c and r equals 0. Okay, so that gives us integral from 0 to pi over 2. C cubed over 3 d theta. So we're going to take our c cubed over 3, multiply that by theta, and then that gets evaluated at pi over 2 and then at 0. So that gives us a mass of pi c cubed over 6, and then from there we can jump into calculating x bar. So x bar is going to be 1 over the mass times the double integral over r of x delta dA. So 1 over our mass is going to be 6 over pi c cubed double integral gets set up same way as before. So we'll do that in a minute. And let's just think about our x delta dA. Okay, so let's draw our polar coordinates here. Let's say we have a point xy, like that. R, length of the hypotenuse, and theta, our angle here. So remember, if you're trying to get x and y are just going to be the horizontal and vertical side lengths here in this triangle. So x is going to be r cos theta, and y is going to be r sine theta. Okay, so that means x value, r cos theta, delta we already said was r, and dA we said was r dr d theta. So we could actually simplify this integrand here. Let's just call it r cubed cos theta dr d theta. Okay, and then we can put our limits of integration on there, same as we did above. So we set our radius values for our region, we're going from 0 to c, and our theta values, we're going from 0 to pi over 2. So with that, we're good to go with our integration. We've got 6 over pi c cubed. Keep our outside integral and outside differential on there. We're going to integrate with respect to r. So we'll have r to the 4th over 4 cos theta, and this is going to get evaluated at r equals c and then r equals 0. Okay, so we've got our constant out in front, we've got our integral and our differential on there, and let's just evaluate at r equals c and then r equals 0. We're going to have c to the 4th over 4 cos theta, and then to finish this off we just need to do our integration. So keeping our constant at the front. Now integrating with respect to theta, we're going to have c to the 4th over 4 sine theta, and this is going to get evaluated at theta equal pi over 2 and theta equals 0. So that's going to work out nicely because sine of pi over 2 is 1. So we're getting 6 over pi c cubed times c to the 4th over 4, which if we do just a little bit of simplifying, cancel a factor of c cubed from the top and the bottom, and we could cancel a factor of 2 also from the top and the bottom. So 3c over 2 pi is the coordinate for x bar. And remember, we said by symmetry that x bar was going to equal y bar. So here we have our answer coming up. Coordinates of our centroid, x bar, y bar equal 3c over 2 pi for both those coordinates.